Welcome to this lecture. So, we were looking at unsupervised learning methods, where the idea is to estimate the marginal density of data without having any labels. We saw a few methods to do that. One was clustering, okay, where we group the data, or we group the data into clusters or sets of unknown labels to start with. And we saw that this can be seen as a special case of learning a latent variable model with discrete latent variables. Then we also saw a few examples of learning embeddings or representations in an implicit way using linear or nonlinear models like neural networks. If you use linear models for learning embeddings, one of those methods is what is known as the principal component analysis, which can also be used, in fact, which can also be used for dimensionality reduction. Now, if you look at the popular literature, the moment people talk of PCA, they say that it is a dimensionality reduction technique. So, to me, every unsupervised learning method that has a latent space can be used for dimensionality reduction. So, in the PCA formulation, there is no hard and fast rule that we have to restrict the dimensionality of the latent space to be less than that of the data space. You can actually have it exactly the same as the data space as well, but a byproduct is that you can reduce the dimensionality of data, right, as a byproduct, and PCA is often used in that context where you are given some data and you want to reduce the dimensionality of data. PCA is used for that particular purpose. We also saw that one can use techniques such as autoencoders, where there is a neural network and there are two neural networks, one called the encoder neural network, the other is the decoder neural network. See, in literature, typically when we talk of encoder-decoder architecture or encoder-decoder networks, we talk of a latent variable model, okay, and a neural network that projects the data onto the latent space is referred to as the encoder network, okay, and the neural network or any function that takes the latent space and projects back to the data space is called the decoder network. So, this is the standard nomenclature across different architectures and so on, right. So, encoder is projections from the data space to the latent space, and decoding is projection from the latent space to the data space back. That is why one side comment is, we will see this later in more detail, decoders can also be seen as samplers, because the output of the decoder is a sample from the data space, right, and that is why you have these terms which are called decoder only models, encoder decoder models and so on. So, encoder decoder models are the one where you have both the capabilities, meaning given data you can get an embedding, given an embedding you can get the data. So, that is encoder and decoder together. So, BERT is one such architecture where you have both encoder and the decoder. Okay. The decoder only architecture is the one where you do not have a projection from the data space to the latent space, but only from a latent space to the data space. Okay. Most of the modern day LLMs, large language models, are decoder only models. We will see this when we look at the generative models part. Okay. But the general idea of unsupervised learning in the encoder decoder architecture is that you have two functions, one which projects the data space to the latent space, okay, and the one that projects the latent space back to the data space. So, why do you use encoding? Encoding is used for multiple purposes. One is dimensionality reduction, right. If you make the dimensionality of the latent space to be less compared to that of the data space, then post training you take any data point, pass it through the encoder, get an embedding or a representation which has lesser dimension compared to the data dimension. So, that is using encoder network for dimensionality reduction. Okay. The other reason that you would want to use that is for embedding or feature extraction, where you do not want to deal with the entire data space, but you want to work on a representation or an embedding space. So, you can use this as the embedding space. Okay. The decoder network is used typically for generation or reconstruction, because you start from the latent space and get back to the data space. Now, there are a few more nuances that can be imposed on top of it, and one of you was actually asking the question. See, we know how to regularize, no, and these networks are not outside the purview of regularization. You can still regularize these neural networks as well. And we saw two types of regularization, remember. One regularization was regularizing the parameter space. The other type of regularization was that you can regularize the outcome of the intermediate layers of the neural network as well. Do you remember that? Right. So, we can regularize the output of the encoder network to follow a certain distribution. Do you see what I mean? Suppose here in the usual encoder-decoder architecture, the distribution that this particular random variable can take is not regularized, in the sense that the distribution of this z can be anything. In fact, what does it depend on? What does the distribution of z depends on? It will depend on the parameters of the encoder network. See, x is a random variable and encoder is a deterministic function. Neural networks are deterministic functions. So, when you transform a random variable from one space to the other, its distribution changes, and it depends entirely on this function that the encoder is imposing. Now, if you want to control what distribution that the z is taking, I can actually regularize the z by saying that, look, you encode the data and reconstruct back, but also ensure that the z follows a particular distribution of my choice. So, that is what the basic idea of this famous methodology called variational autoencoders. So, we will see that. So, the idea basically the idea that I wanted to say is that you can regularize an encoder-decoder architecture as well, the unsupervised learning architecture, where you constrain the distribution of the intermediate representation to follow a particular function. That can also be done. Okay. Now, we saw all this. Now, we will go to a different paradigm of unsupervised learning, where the problem is still the same, right. So, the problem is that given data, and my x is in RD and they are drawn IID from Px. Estimate Px. Okay. This is the problem that we are solving in unsupervised learning anyway. Now, so far how are we estimating this Px? We are using the same methodology of KL minimization, which is the maximum likelihood estimation, where we assume a parametric form on Px and then we use whatever the standard architectures are, and then we find the estimate the parameters by maximizing the likelihood. But the question is, in some of the cases, some of the forms of p theta that we assume on Px, maximum likelihood estimation becomes intractable. So, we already saw one example for that, right, which is the mixture densities, where we had an EM algorithm where we built variational methods to do that. But is there another way to avoid maximum likelihood altogether is the question that the noise contrastive estimation tries to answer. Now, we also know that classification or discrimination is an easier problem to solve than estimating the marginals. Estimating conditionals is easier than estimating marginals. Why do you think so? What do I even mean by easier? See, when you suppose you are solving a classification problem, right, the conditional density that we estimate, which is P of y given x, okay, are Dirac deltas, no, they are discrete densities. So, I am sorry, they are not Dirac deltas, they are discrete densities. For a binary classification problem, it is only one parameter that you want to estimate finally, because P of y given x can be quantified using one parameter, right. So, any classification problem is compressing, okay, the data space, partitioning the data space into discrete categories, which is easier. Estimating the entire marginal is difficult. So, what do I mean by that? Suppose you have a classification problem, okay, and your data is in RD and you are solving a binary classification problem. Now, as long as all the data points that correspond to a particular class are collapsed and mapped into one label, we do not care, okay, whether given particular points are completely preserved when you are estimating the density. Do you see what I mean? See, what does a classifier do? Classifier will separate the data space into non-overlapping regions, isn't it? Now, as long as your data point is identified to be belonging to the correct region, we do not care where the data point is within that broad region. So, this is learning a discriminant function or a classifier. But if you want to estimate the marginal, then it does not suffice if you only say that the data point is in this particular region. You will have to exactly say where the data point is. Otherwise, you will be confusing between two data points. In a classifier setting, it is okay to confuse between two data points as long as they belong to the exact same class. Do you see why? You see that, right? So, now that is why discriminative models are easier to train than generative models. And in other words, estimating the conditionals, label conditionals is easier than estimating the marginals, data marginals. And you see why, right? Geometrically, all we are asking is in the conditional density estimation is that tell me whether this data point belongs to a particular region or not, okay. But for the marginal density estimation, which is the generative modeling, we will have to say where exactly this data point is, we will have to estimate the entire density. So, that is the difficulty. Now, why did I say that? Now, the question that the authors of this paper asked is there a way, okay, that we convert the problem of marginal density estimation into a conditional density estimation problem? Because we know how to train classifiers. Now, can we catch the problem of estimating the marginal density in this situation, which is the unsupervised learning problem? Can we formulate that as a classification problem and still end up estimating Px is the question? Okay. So, let us write that down. So, that is the exact objective of noise contrastive estimation. Can a classification framework be used to estimate the marginal? Okay. Now, as with any density estimation technique, so NCE also starts by assuming Px belongs to a parametric family of densities P theta, where theta are parameters. Okay. In ML estimation, now P theta is estimated by this usual KL minimization technique. This is what we do, right? We minimize the KL divergence between the true density and the parametric density, and this is all we have been doing the entire course. Now, in noise contrastive estimation, we do not do this. So, what do we do is the question, right? So, let us look at how it works. Okay. in NCE assume p theta to be of this particular form, let us call that p theta dash divided by z, where c is the normalization constant. So, assume your parametric density to be having this particular form, that there is a function p theta dash and you divide it by some normalization constant. So, this p theta dash is a function which is from R d to R plus, okay. It is any function that takes that maps from the data space to positive real numbers, but this is not a valid density function because it does not integrate to 1. Now, p theta integrates to 1. To ensure that p theta dash integrates to 1, you will have to divide it by some normalization constant z, okay. So, what is z by the way? It is the integral of p theta dash over dx. So, whatever this function integrates to, divide that by that constant, and you will make that a valid density function. Now, what happens is, by the way, these are also called see, this form of assuming the parametric density is pretty common across multiple models. One family of models which uses this sort of a parametric definition of densities is what is called as energy based models, or EBMs, okay, where this p theta dash is also called as the energy function. So, call that as E theta. So, for those of you who have studied some physics, right, this is also called the Gibbs distribution, right. So, you call this as the negative of energy, and you say the more the energy, the less the probability of finding a particle, and vice versa, right. Typically what happens is, when you assume the density function to be of this form, finding of this normalization constant becomes a big issue. Why is that? It is because it involves an integral over the entire data space which is intractable. So, now noise contrastive estimation also gives you a way to avoid estimating the normalization constant, okay. Uh, if you take the maximum likelihood estimation, so suppose you assume p theta to be of this particular form and then do an ML estimate, then z comes up everywhere in the estimator. Now, we will see that in the noise contrastive estimation as an estimator, okay, z will just disappear. So, NCE serves two purposes. One, in the density models where you have an intractable normalization constant, we will have to get rid of the normalization constant in the estimator. The second thing is, we will have to model the marginal densities using a classification approach. So, NCE will serve both these purposes, that is the idea, okay. So, now we will assume p theta to be p theta dash divided by z and see what happens now, and I have been using this word estimator all the while, right. So, what is an estimator? I am assuming that you people know that. Suppose we have, what are we trying to do here? We are trying to estimate the underlying density function. So, whatever function of data that we look at, okay, which is formulated to get an estimate of the underlying density function is called an estimator, right. So, ML, the maximum likelihood estimator that we get, which the theta, the p theta that we get by solving this optimization problem, right, is also an estimator. It is called the ML estimator, and we also saw map as an estimator, which is a Bayesian estimator. So, this is another type of estimator that we are looking at for the density function, which is called the noise contrastive estimator, okay, right. So, now let us, with these definitions we are ready to define what it is. Now, in NCE, in addition to Px, define another density function Pn which is not the same as Px. Take any arbitrary density function Pn, okay, which is not the same as Px. Pn, because you can call this as the noise density. The name noise contrastive estimator is coming from this particular density. So, this you call this as noise, I mean, because see what is noise after all? Anything that is not music is noise. So, what is music? It's very subjective, right? I mean, what can be music to you can be noise to someone else and vice versa, always. So, here in the context, whatever we are calling as data is our data distribution Px, and whatever is not the data distribution is the noise distribution, that is it. So, that is why I said some distribution that is not the same as Px, okay. So, typically we make some choices on Pn, that is okay, but theoretically speaking it can be some density that is not the same as Px, okay. Now, sample m points, so call it y1, y2 up to yn, let us call this d dash m points, right, yeah, ym from Pn. We have n data points, we also sample n data points, m data points from Pn, okay. This is what we have. Now, let us denote another data set du as u1, u2 up to um plus n as the union of d and d dash. So, I create an extended data set by taking a union of x the samples of Px and samples of Pn, okay. I will tell you what the entire story is and then we will do the math. So, what we will show right now is that if you build a classifier that would solve a binary classification problem with labels denoting whether a given sample is coming from Px or Pn, then that classifier estimates Px is what we will show. You see that? So, all we are trying to say is if you know how to differentiate music from noise, then you know what the music is, right. So, if you know how to classify between samples of Px and samples of Pn, which is solving a binary classification problem, then that becomes an estimator for the underlying density. That is why the name noise contrastive estimation. So, this is estimation via a contrastive learning. Okay. What are you contrasting between? You are contrasting between the samples of data and samples of noise. Now, you know that this is data and this is noise only if you know what the underlying density is. So, makes philosophical sense also, right. So, if you want to learn a particular behavior, you will have to learn what this behavior is not. That is exactly the point. That is what the rest is math. We will show mathematically that solving a binary classification problem, okay, with these as labels will lead us to an estimate on Px is what we will show. That is why the name noise contrastive estimation. It is pretty amazing, right? It is very simple. We are not trying to maximize the likelihood or anything. All we are trying to do is creating a pseudo classification problem where we are trying to discriminate between whether it is data or noise, okay. And if you do that, you are effectively learning what the underlying data density is, okay. We will show that now mathematically. So, du is the union of these two data sets u1 through um. So, now let us assign binary class label let us call that C j such that C j equal to 1, let me write it here, equal to 1 if u j is in D, it is equal to 0 if u j is in D, what did we call it, D dash. Yeah, this is how we label it. So now we can create these labels, right. We can create these labels because we know what point, what data point in data set du belongs to x and what belongs to n, pn, right. So that is why we can create these labels. Now consider the class conditional densities. So P of u given C equal to 1, what is this equal to? So what is this? The density of the data points u given the class is 1 should be Px, no. So we actually will call this, we will model this as P theta dash, the unnormalized, as unnormalized density, okay. Then hold on, should it be the unnormalized density or the, should be normalized one, right, it is P theta, yeah, it is P theta of x. And P u given C equal to 0, what is this? This is Pn, correct, yeah. Okay. We also have, what is this equal to? P of C equal to 1, what is the prior here? The number of samples coming from the first class is n by n plus m, correct, yeah. So, and then P of C equal to 0 is m by n plus n, correct. Okay. So therefore, use Bayes law and write the posterior of this. Why do we need this? Why do we need the posterior? Because remember, in a binary classification problem, what do? We estimate P of y given x, okay. So what is that? We know from Bayes law that this is equal to P theta divided by P theta plus Pn. Oh, we also have the prior, no, it will come here, I think let us write that as nu, where nu is equal to m by n, it is okay, no. See, it would be, let me just tell you, it's simple Bayes law, this should be P theta times n by n plus m, and there will be an n by m plus n term here, and here there will be an m plus m by n term. So I divide everything by whatever there is in the numerator, so an m by n term will remain here. Do you see what I am saying? Simple Bayes law, all of you got this? No? Okay, I see a lot of blank faces, let me do it again. Don't, you are making me write down the Bayes law, So, this is u given c equal to 1 times p of c equal to 1 divided by is it okay now p theta times n by m plus n divided by p n times m by n plus m plus p theta times n by m plus n, correct. Now what? That is exactly what I wrote. So, this is p theta divided by p theta plus nu times p n is equal to m by n. This is the posterior of, correct, and similarly the posterior of c equal to 0 given u is nu times p n divided by p theta plus nu times p n. Okay. Now, in maximum, suppose we want to estimate p of c equal to 1 given u, what do we do in a classification problem? We maximize the likelihood of p of y given x. So, in ML estimation, the objective is to maximize the likelihood of the posterior. Okay. Now, if I have to write that likelihood of the posterior, what is that equal to? It is equal to plus this is some exist everywhere 1 minus C I times log of this is the standard binary cross entropy, right. So, we want to maximize the log likelihood or minimize the negative of that log likelihood. Now, if I plug in all the definitions that I have written here for p of c equal to 0 given u and p of 0 equal to 1, I can write this as log of h theta of x I plus log of 1 minus h theta of y I, where h theta is 1 by 1 plus nu times e power minus, just looking for a letter, okay, let us call that f theta, where f theta of x is log of p theta of x minus log of Pn of, okay, let us call this as u because we have been using u, evaluated at this u of p. Come again, what is the question? This one, is it? Yeah, so this comes from, see, our data set u here has y, is not it? Whenever it is 0, it is coming from d dash, those are the noise samples, okay. So this is the final estimator that we, or the loss function that we will use to maximize the likelihood. So what is this? Now we will look at this, we look at this expression, okay, and if you see h theta as a function that is taking from, that is taking samples from x and y and mapping it to a real number, okay, then this f theta of u, okay, or rather h theta is a composite of this function f theta, okay, which is estimating the difference between the log likelihood of these two, and there is a sigmoid on top of it, okay. Now suppose I model this f theta of u using a neural network and then put a sigmoid at the output of it. What am I trying to do is trying to classify between the samples of u and x. So look at this expression, right, this expression is nothing but the loss function for a cross entropy, when it is exactly the binary cross entropy for a binary classification problem. Now if I treat my h theta as a neural network which has a softmax at the output of it and then just solve a classification problem by solving this particular function, then I will be maximizing the likelihood of p theta of y given x. So what is the likelihood that we just computed? It is p of c equal to 1 given u. What is that? It is the likelihood of observing the, or the input data point coming from the actual data set but not noise. Suppose I build a neural network, okay, which would maximize this likelihood. What am I effectively doing is trying to solve a binary classification problem that would classify between the samples of data x and samples of noise y. Do you see why? Because even in a neural network, suppose a neural network is trying to solve a binary classification problem, what is it doing? It is trying to maximize the likelihood of the label y coming from class 1. That is exactly what this loss function is, isn't it? If you look at this loss function, what is this doing? This loss function is saying, what is the, this is nothing but binary cross entropy. Can all of you see this? Yeah. So what does binary cross entropy say? Binary cross entropy is coming from maximizing the likelihood of the distribution of the Bernoulli random variable that signifies whether a data point is coming from class 1 or class 0, that is it. Okay. So far what did we show? So far all that we showed was that maximizing the likelihood of a random variable that would determine whether a given point is coming from the data or not is equivalent to solving a binary classification problem that would classify between the data and the noise points. That is what we have shown so far. All of you convinced? Now there is one final piece that is missing, which is that this loss function, which is maximizing the likelihood of observing the data sample, estimates the underlying data density, right. That is not something that we have shown, which is exactly what we want. We will show that in a while. Any questions so far? That so far what we have done is, given data, we constructed another pseudo data set and solved a binary classification problem that would classify between the points from the data distribution and points from the noise distribution. That is what we have seen so far. Now we have to show that this loss function, which is the cross entropy classifying between the samples of the noise and the data, will estimate the underlying data density is what remains to be shown, which is what we will show now. Okay. So, let us move on to the main result of the NCE. Go on, yeah.
The sample of noise is like data integrated with noise, or it is pure noise.
Yeah, the question is how do you define PN, right? We will see there are multiple ways to do it. It's most, I mean, different empirical methods do it in different ways. So I'll discuss a few methods to do that. Okay. Now the final NCE estimator. We will stop here and continue in the next lecture.